I'll go ahead and start the streaming since it looks like everyone's here. Where's the candy? Candy's in the back, so yes, please help yourselves. The objective is to get rid of it so that I'm not pounding it in my office in the mornings while I'm sitting here, as I did today. So we had an interesting thing happen over the weekend. On Sunday night, my husband comes in and he's like, so I got an email about the homework system. Yes, so did you see it was down? It was down all Sunday. Yeah, apparently the server that we subscribed to got taken over by hackers who were demanding, I guess, Bitcoin or something for the data. Like it was straight out of an episode of CSI or something. And I was like, okay, I don't know how to handle this situation, but thank goodness there's no homeworks out right now, so it's not like a major chaos. And then Monday morning, it just came back. So it's back.
She's not going to must have paid the ransom.
I was like, well, I'm not paying for it because I've already downloaded all my data sets. So I was caught up as of Friday. So it was great timing for the hackers. So hackers, if you're listening, good work on that. If you could hold off until after December 12th or so, that would be great. I'll give you a bonus Bitcoin. But since it was working, I went ahead and put up your next homework. Oh, good. Yes. Correct answer. Yes. And I also extended already the deadline for it. So it is not due until the Friday before Thanksgiving. So instead of that. So all next week. We're going to finish the material that you need to be able to do it today. I will warn you that it looks long in terms of the number of things, but that's because I'm going back over stuff that I saw folks have problems with so that you get a chance to practice it again. So this is actually just 4 models. There's very little original coding that's required. It's just more interpreting the results and stuff. So homework 5 is available to you. Nothing is happening during Thanksgiving week and nothing is happening when you come back. So I hope that you are able to take a real legit break. However that looks. If it's going somewhere, great. If it's Netflix and chill, even better, right? My entire family is coming to my house. But we've already ordered Thanksgiving dinner from Hy-Vee. So that is how you do it. All right. So we've got that. And then just 2 more weeks after next week, things are winding down. So kind of sad. Let's see. Registration is happening for the next classes. I've already got 9 people in my next class next semester, the follow-up to this one. So I'm excited about that because our dean says we're supposed to have 8 in order to have the class make. So hooray, it's going to happen. If you know of folks who want to take this class, spread the word. I'm still looking to fill a few more chairs in that one. After this year, I'm anticipating offering this class every fall, not twice a year. So that, but hopefully then we'll have a regular sequence of this plus the generalized one after that. So let's see, quizzes. Let's do this. So yes. So quiz 1 here. In what situations, what types of predictors and their type of relationship to a quantitative outcome would a Pearson correlation be sufficient to describe the bivariate relationship of the predictor to the outcome? So I've read your answers. A lot of you picked up on this. When would this be sufficient? What kind of predictor, what kind of relationship? Linear. And if it's linear, then what kind of predictor is it? Quantitative or binary, yes. And so asterisk to that, if you log transform your predictor, then a linear relationship of a log transform variable is an exponential curve, but it's still only one slope. So it's the same idea. Anytime it's a linear relationship with the predictor can be transformed such that that creates a different shape. But one slope does the work. That's the big picture. So in what situations then would you need to estimate a general linear model instead?
If you have more than 2 quantitative predictors.
Yeah, more than one slope. So that takes a lot of different forms. More than 2 predictors. What about other kinds of quantitative predictor relationships? Like the thing you just did in your last homework. Piecewise or quadratic, yeah. So if you need more than one slope to describe the effect of a single predictor, that also happens in a model. When is another instance in which you would have more than one slope to describe the effect of a single predictor?
ANCOVA?
Yeah. More generally, what kind of predictor? Categorical, like golf, right? Control versus mini golf versus regular golf. Yeah, the story behind that, by the way, is that giving you regular golf training messes up your mini golf game. So that was the driving influence. The last time my family got together to play mini golf, that was what my dad claimed. Anyway, his game was off because he had been regular golfing too much. So there you go, Dad. You said it, not me. So yes, more than one slope to describe the effect of a single predictor or more than one predictor in the model, then you need a general linear model to quantify those relationships. So good. Questions on that?
Could you repeat that last part?
Sure. So we'll do the whole thing here. In the situations in which a Pearson correlation would be sufficient is when you have one slope to describe the effect of a predictor. So that would be if you have a linear effect of a quantitative predictor or a binary predictor in which there can only be one difference. For anything else, so whenever you have a nonlinear effect of a quantitative predictor, such as quadratic or piecewise, whenever you have more than one predictor in the model, or whenever you have a categorical predictor that takes multiple slopes to describe all the possible group differences, then you need a model. Other questions? All right, number 2. So this one, folks got half of it right for the most part. In what situations would you expect the unique effect of a predictor slope to differ from its bivariate effect? So bivariate, when it's just by itself, right? Such as when you have a Pearson correlation or a model in which that's the only predictor. Unique is when you put predictors together in the same model. So when would bivariate and unique be different things? Not just when they're in the same model, but what else has to be true?
When the predictor doesn't get individual credit for what they have in common with predicting Y.
So when the common, that's the key. So if a predictor shares covariance with another predictor, if it's related, then the extent of their prediction can overlap, and they don't get credit for what's overlapping. They only get credit for the common part. So if you had 2 predictors in a model that were not related, their unique effects would be their bivariate effects. It's only when they overlap that they change. And overlap means covary, correlate, share common variance, are redundant, are not mutually exclusive. Any of those would be acceptable to describe that idea.
So not they clean to the same room, because that's
I will take that as well. They clean the same room.
my whole life it'll be like Kate and Randall clean the family room.
Yes, and thank you for pointing out that Pearson is not the same Pearson as Pearson correlation. I was like, oh, Jesus, how could I have not seen that one coming? It is the Pearson family, though. That is what it is. It's just unfortunate that Pearson shows up in about 4 different other things in this class. But yes, so unique and bivariate are not the same to the extent that the predictors have something in common. That is the key. And last but not least, this is also a throwback question, but I thought it's good because I want to make sure you have this by the end of the semester. What is the relationship between effect size, the statistical significance of that effect against a null hypothesis of 0, and sample size? So most of you got this reasonably correct. So with more sample size, what happens? Effect size is not necessarily greater. And effect size is greater. So let's say if sample size is greater, what happens? More likely to get significance. So for the same level of effect, the more people I have to find it, that effect is more likely to be aberrant, to be significant. The more effect you have, the more likely it's to be significant too. But effect size has nothing to do with sample size per se. That's the rub. That's why we need effect size, because you can have an effect that's significant and it could be not what we call practically significant, or it could have a very small effect size such that we don't really care that it's not expected, that it's different than 0. So we want to be able to quantify any effect in its original metric, such as a slope of 6. We have no idea if that's good or bad. Some kind of effect size that goes with that 6 that puts it in a metric that we all know what to do with, like a correlation metric that goes from -1 to 1, or a D metric that goes from 0 to infinity. And then we can look at power, which is the probability of finding an effect that's there given that sample size and effect size. That's useful for study planning. Okay. I feel like the M&Ms are hitting my bloodstream and I'm talking really fast. So, is any of that you'd like me to say again or more slowly or more coherently? Hmm?
The last question.
The last question? So, significance is more likely if you have more people and more effect size. But effect size is a metric that quantifies the size of an effect in a way that we can all appreciate, that's not scale dependent. So when you have a significant result, it doesn't necessarily mean you have a big effect. It could mean that you have a lot of people. So that's why we need both. We need to know what the significance level is as well as what the effect size is. The effect size has nothing to do with people. Is that better? All right. Other questions on any of this? All righty. If not, if you think of any, let me know. Otherwise, I will shut this part down and we'll go to where we left off in example 6. Yeah, we're in example 6 on page 11, in fact, is where I'd like to start. So I posted the new version of the handout that has the equation that I accidentally forgot last time. So far in this handout, what we had done is look at the effect of each predictor separately. So we tested for the potential for nonlinear effects of age, which is a quantitative predictor, as well as nonlinear effects of grip strength. Neither of those were significant, indicating linear is probably sufficient. We looked at gender differences in our cognition outcome, as well as dementia group differences, in which the dementia groups, I'll review the coding for you here real quick, because that's always helpful. So we have 3 groups: no dementia, future dementia, and current dementia. No dementia is the reference, so in the contrast, they both get the 0. NF is the difference between none and future because they get the 1. And NC is the difference between none and current, so they get the 1. How would this change, by the way, if I instead wanted the second contrast to represent the difference between future and current? Homework question. Any ideas? So right now, I know what these things mean, not just because I said so, but because of the way I set up at the 0s and the 1s. So if we looked first just at this first little column right here, the NF column, right? It lumps together none and current, and it differentiates it from future. That means we need something to unlump none and current, right? That's where the second one comes along and does just that. So if I instead wanted this second one to unlump future and current, what would I need to do? Any guesses?
Take off the else.
The else doesn't do anything bad in this case, but it isn't strictly necessary either, given the way that I wrote this. You don't need the else's.
Would you put 0.5 for the NC one, the current?
This? That would only get me half of the way there. I'm going to let you guys think about this because there is an example doing that we've already gone over, just in a different context. So I'm going to let that percolate, okay? But just as a general concept, how you split up your groups is completely up to you. Whatever sorcery you engage in, and yes, I'm going to keep that word, if that's all right. It's your sorcery to be able to figure this out. So because of the way I set this up, I know that this is none versus future and this is none versus current. This is the most common way people do things because it's the most straightforward, but it's not the only option. Okay. So back to page 11. Okay, so we got some new stuff here to look at. Here's our combined model. So the question is, what do these effects look like now that each of them has to compete with the others? So we're going from bivariate to unique. So to what extent does it still matter how old you are after you control for your physical health, your dementia status, your gender? To what extent does it still matter how strong you are after you control for your age, your gender, etc., etc.? So transitioning from bivariate to unique is after controlling for the others, do each of these predictors still matter? And do they work together to create a significant model? So to put them all in the same model, there's nothing different than what we've already done. So cognition is the outcome. In SAS, it's equals, and you list all of your predictors right here. In Stata, the first word after regress is the outcome, and then you list all of your predictors. Same here. Oh, this is a hodgepodge of code here. By the way, in Stata, do you see this C dot here? This is a default. It indicates that these predictors are being treated as continuous. I don't entirely know when it's necessary and when it's not. So sometimes it yells at me and I stick it in and it's happy. So what happens here when you see things like this is a hodgepodge of me borrowing across different codes where I've used my C's and where I haven't. I need to fix this to be consistent, but I will add them to these places here because I think it doesn't like it if you use it sometimes and not others. And it was originally when I started writing lincoms where it started yelling at me. C dot. C dot. There is no analog to C dot in SAS. If you don't say anything about it, it's treated as a typical quantitative or continuous predictor. There we go. There. Got that. All right. So some new stuff. Mean differences across the groups. You've seen this before. So given the way that I've coded dementia group, 2 of these are already given to you in your output. Which ones are they? Yeah, the first 2. I wrote these here as a trail of breadcrumbs. I didn't need to write them. It's just a habit I've gotten into whenever I list my group differences and I want them all in the same place. It's the third one, the difference between the non-reference groups. That's what the model does not give you in this case, in which you would have to ask for specifically. So those you have seen before, these are new. So contrast and test. These do the same thing. Contrast is how you request multivariate Wald tests. So do you remember the rules about what test you get versus what letter? So if you're testing one slope, you get a T. If you're testing more than one slope, you get an F. So these are asking for F tests. It's when you want to lump something together to test a set of things against 0 at the same time. We haven't had to do this yet because it's already been done for us in asking for the model R-square. That is an example of one of these. So I wrote this out so that you could see what it actually is doing for you behind the scenes. So this first contrast right here, as well as this test right here, what that is doing is asking for the test of the model R-square. What you do is list every single slope and what you want it to do. So you want one of them, I want one of these, one of these, one of these, one of these. And note the commas delineating these. That tells it how many numerator degrees of freedom the test should be, how many slopes you're testing at the same time. So I listed 5 terms on here. So I'm asking simultaneously, are these 5 things different than 0? And that works out to be this. That's what it's doing. So my F value of 41.75 for the model, that tells me that my R square is significantly greater than 0. That is now also here because I just asked for it. So if it's already given to me, why am I asking for it? Because you may want other versions of it. And there are certain software packages where it's not provided by default and you may need to ask for that. So for instance, here's one that I also want to know that is not provided by default. Whether or not there's a significant overall effect of dementia group. The model parameters give me 2 out of the 3 possible differences. I want to be able to lump them together to get some indication as to how group is significant as a whole. And that becomes more and more useful the more groups you have and the more possible group differences there may be. So in this case, all I listed on the statement are the 2 contrasts for group. And so the commas that delineate numerator degrees of freedom, in Stata, it's the parentheses that do that. And so we're setting them equal to 0 as a more implicit or explicit way of writing this. So if all I had in the model were these 2 dementia things, if that's all there were, then this line would give me the model test for the R square. Because I have more things, this is giving me a joint test of the unique effect of these 2 terms. So there is, come back here. There is something that you may hear about at some point in the rest of your training called stepwise regression. Have you heard of this before? Yes, Terry, what's the context in which you've heard of it? No, you nodded.
Yes.
Heard it. No idea what the hell it means?
Heard it.
Yeah. Heard of it, no idea what the hell it means? Okay, great. So it's the idea that you enter terms into a model one at a time to see if each new term adds significantly to the model. Yeah, sound familiar? It's coming back? Yeah. So if you add only one thing, you know that that new term, the one thing, if it's significant, the R square is bigger. There's a 1-to-1 correspondence there. But if you're adding more than one thing at the same time, such as adding these 2 effects of dementia group, you don't know which of them made the model bigger. Or if it's the third one that's actually implied by these that you're not directly given. So this is a way to get all of the information that you would have to get separately through stepwise regression simultaneously. You can use these contrast statements to lump any terms together to know if the model does better with that lump of terms than without it. Because once these things are all in the model, they're all treated the same. They're all unique effects controlling for everything else that's in the model. So order doesn't matter in the eventual model. So what would I put here, for instance, just to generalize this construct? If all I had was, say, let's say I just reported this model in my paper. Because what happens a lot of the time when you run models is that you'll run 7,000 models and only like 2 will make it into the paper because the paper can only be 25 pages or whatever. So you can't show all the legwork that you went through to get to that point. So some reviewers, if that's all you said, well, I don't think that these predictors belong in this model and they should do a stepwise regression to see if they help the model. Okay. Sorry for confusing you, even though you're dead wrong. But let me go ahead and get that F for you so you shut up and publish my paper. What if they're mad about, let's go with age and grip. How would I demonstrate that age and grip contribute significantly to the model? Yeah, I'd put age here. 85, grip 9. That tests that chunk and whether those two things working together contribute to the model. Now, age and grip don't have anything to do with each other other than that someone might think of them as control variables. Remember control variables? Remember that from the beginning? Yeah, you're laughing. What does a control variable mean?
It's like you're taking that out and you're looking at the rest of it.
That's what people do with them. Remember my definition of control variables? It's a predictor that someone else cares about, but not you. So for instance, I used to live in this world of cognitive aging in which this data set story came from. Age has to go in your model. It is the control variable that you must have or no one will take you seriously. Every field has a control variable like that. So if you're reading a study, what do you have to control for in the stuff that you read?
Oh. For mine would be like demographic factors.
Demographic factors. So if you don't control for student
Race.
Race is a big one? Okay. How about in EPLS folks? In the papers you read, what do you have to control for? Someone's going to yell at you. SES? Yeah. Anyone else? Counselors?
What degree is it?
SES? Yeah, there's just certain things that it's like, well, duh, that's related. You have to show that you're doing something unique besides that, right? So it's convenient sometimes if you can lump things together to say, aside from the controls, my things that I care about matter, or these controls as a set don't matter. So the natural time to lump things is when they are parts of the same idea, such as these two contrasts that go together to represent dementia group, but you can do this for any combination of variables as well. So I will ask you to do such a thing in your homework, in fact. So this is your example of how to do that. Okay, how are we doing? Okay, so let's look at some of the results and then we'll go over the last line here, which is a different purpose. So here's my model. As a whole, my 5 slopes significantly account for variance according to my F. Hooray. R square. Let's do a review. 2 definitions of R square. Who wants to play? Okay, Kelly's looking at her notes. I'm going to cold call on someone else. Dun, 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 dun. Okay, Terry wants to play. Go.
Proportion reduction of variance.
Proportion reduction of variance. Okay, good. That's one. That's the easy one.
Yeah, I know.
But that's the one that like 95% of people would say. So that's cool. The square of the correlation between something and something. I'll give you a hint.
Y and white hat.
Y and white hat. What's white hat again? Predicted, yes. So that latter definition will generalize to more complex models as well. So how well the model predicts your outcome. You ask it to predict the outcome, which I haven't shown you much, but that's coming in the next unit. Create a column of predicted outcomes, square that column with the real one, that's your R square. Technically, this number comes from a ratio of sums of squares and not mean squares, but it's close enough to where the distinction really doesn't matter. Then we get down into some of the other stuff here. So I'm going to skip effect sizes for right now and head back down here. So here are my results. Okay, so intercept. Intercept is my UR here sign, right? It's my reference point for the model. It should be somewhere in your data. Middle is useful, but doesn't have to be exactly in the middle. So 29.3-ish is my expected cognition for what kind of person will go down the list? Somebody who is age 85. Is a man. Yeah, it is, but men are the 0. Yeah, I just left out the V because it's like men versus women is the way I do this. And for these two?
Not
No.
in the future.
Yeah, not going to be demented. diagnosed with dementia. Excuse me, I can't say demented, that's incorrect. Not going to be diagnosed with dementia. So that person gets 29. Now, each of these effects for now, these are slopes, right? Now, I am going to very quickly stop saying the word slope and start saying the words main effect. I'm just warning you. You like those words? No? Like slope better? Main effect slopes? Can I put them together? Because the idea is that each of these is unconditional with respect to the others, or marginal. Meaning, this age slope is the effective age no matter what level of grip you have, no matter if you're a man or a woman, and no matter what your dementia status. Likewise, this grip slope is no matter what your age, your gender, or your dementia. Starting later today or Thursday, that is not going to be true anymore. We're getting into the world of interactions. Yeah, Jeff, do you like those? I saw that face. It's like, no, but that's important because then you can test moderation. Moderation is a big buzzword. That means interaction. But yes, these are main effect slopes that are marginal or unconditional, meaning that they are not dependent on any other value of these things. So in other words, even if I centered my model such that it was age 90 instead of age 85, this slope is unchanged, this slope is unchanged, this slope is unchanged, this slope is unchanged. So right now, the only thing that depends on your centering is your intercept. That's the only thing right now. So for every year older, what happens to your cognition?
It goes down.
It goes down by that much per year, significantly?
Yes.
Yep. For every pound more you can squeeze, what happens to your cognition? It goes up by that much per pound, significantly?
Yes.
Yep. Who does better, men or women?
Men.
Yeah, men. Yeah, women are bringing us down,
Bring us
right?
down.
And how do I know who's higher? So, coding, right? Men versus women, men are the 0. That means men are the 29. Women pick up the coefficient because they're the 1. So they pick up the -3, which brings them down to like 26. So this is the gender difference between men and women. It's the difference applied to the 1. It's how women differ from men. What would happen if I switched my coding of gender to make the women the 0 and the men the 1? What would happen to this number right here? It'd be positive and it'd be the same. And the intercept would switch to be the 29 instead of the 26. So,
Or it'd be 26.
yeah, that's right. 20. Thank you. 26 instead of 29. This would be +3. So they would just flip. Okay. Now dimension none is the 29. What happens in the future people?
They go down substantially.
They go down by 5. So dementia is bad for you. I wouldn't recommend getting it. Relative to the none people at 29, what happens to the current people? Down a whole lot, 16. And do we know if the future people and the current people are different? Is there anything that I'm pointing to that tells us up here? You'd have to find out, right? Linear combination? That number minus that number? And that's down here. -16 minus -5 is the -10. So that's the missing one. Okay. So each of these then is significant still after controlling for everything else. In a moment, I'll show you a comparison chart of those, but we also got to talk effect size. So here's one way of talking about effect size, semi-partial eta square. Do you remember what that's supposed to be? We talked about this a little bit.
Isn't it like where, like, well, I guess I don't know if it's, that doesn't all add up to equal the R squared, I don't think. Or maybe it does. Okay, just looking at
Doesn't.
this.
Uh-uh.
but it's like breaking it. It's like a unique effects maybe.
Yeah, it's supposed to be, at least my understanding of it from everything that I read, is that this is supposed to be like the chunk of the R square that is uniquely attributable to each variable. However, that can't be true. So I think that works so long as you're not talking about categorical predictors. Because if you add these up, back from the model, let me show you what happened. Here's how I figured this out. We'll go back to the model that just has dementia in it. The R squared from the model with just dementia was 0.17. Here are the semi-partial eta squares for each contrast, and I asked for a new one. So I've added this to this handout since you guys probably last saw it. I just re-upped it when I figured this out so that I could show you. So even if we go with just the two that are in the model, 0.04 plus 0.15 is more than 0.17. So I honestly don't know how to reconcile that because nothing that I read talks about that situation. These things have to work together to delineate the effect of group. And as such, I think the fact that they're overlapping makes it so that these things can't be thought of in the same way as the other variables. So I honestly don't know what to do about that. Effect sizes for these sorts of categorical predictors are tricky. I will let you know if I come up with a better explanation, but I know that that is an overly simplistic one, the semi-partial eta square. But I asked for the missing one right here with a contrast. So these two lines differ only a little bit, but they do different things. So the first one, that lists both of these with a 1 and a comma. That is a contrast that lumps these two effects together to test their joint significance. That's a multivariate Wald test. Like the F for the model is a multivariate Wald test. The second one matches the form of the estimate statement that's used to get the missing group difference. So actually this contrast and this estimate of beta 5 minus beta 4 are redundant, but I figured out that if I asked for it via contrast, its semi-partial eta square shows up in the output, whereas it doesn't show up from estimate. So it gives me a unique sums of squares for that as well as the semi-partial eta square for future versus current. So that's why I asked for that. And I did the same thing in the combined model. Let me find this here. Where are we at? Here we go. Lost it. There we are. So the semi-partial eta square for future versus current is 5%. The ones for the others are right here. And they do not sum to the total. So this is the rub. Standardized effect sizes. I had no idea until I started playing around with all these different versions just how not standardized they actually are. I'm trying to keep it real. Because people treat these things as if they're like written in stone, and they're not even within a kind. So what I did do, more out of curiosity than anything else, is ask for a couple more. So I asked for standardized regression coefficients, because that is a very common thing you will see people do. A standardized regression coefficient as deliverable in proc reg for SAS with the STB option after the model, or by asking for beta in SATA under regression. That gives you the same regression model as if all the variables had mean 0 and variance 1. So here's the solution from SAS Reg, where the last column is the standardized results. And so those are supposed to be within a metric that follows a correlation metric, ranges from -1 to 1, where 0 means there's no relationship whatsoever. However, what don't I have here? All of these are what's given directly by the model. it won't let me ask for anything else. So when I do Lin Commons data, it won't give me the standardized version. When I try to do estimate in SAS, it won't take it. So I can't get that one. So here's a way to cheat. Do you remember at the very beginning of the handout, I made z-scores out of everything? This is why. So a z-score is a standardized variable with mean 0, variance 1. I did that for all the predictors and all the outcomes, and then I ran procGLM. procGLM allows me to ask for linear combinations of my z-score variables, and the same thing can happen in regress. And so then my solution is standardized. These numbers exactly match the standardized solution, and I get the missing one. So if you'd like to get standardized slopes for all of your model effects, including linear combinations, this is what I would recommend doing. Z-scoring, and then run your model again. The other thing that I did throughout this handout is p-values for your effects and use it to compute Cohen's, the table that has our effect sizes directly from those t's, because that's an approach that generalizes to more different types of models in GLM. And so then I made a table. So let's focus on that column versus that column right there. The one on the left, these are the bivariate effects. This is what I got when I ran each predictor in its own model separately predicting cognition. On the right is the same predictor's effect in the joint model competing against the others. So in this case, there's no big surprises in terms of direction. Everything is significant, so I didn't bother printing p-values, but you can see that the effect size is diminished in terms of its original metric. So minus 0.5 for age down to minus 0.4, minus 9 down to 0.6, and so on. There are a couple instances of interesting things, though. Look at what happened to dementia. What happened? It got bigger. Turns out that can happen. I've been trying to say very carefully that bivariate effects differ from their unique effects because differ doesn't imply direction. It is entirely possible that effects can become stronger after factoring in other effects. That is a phenomenon that's known as suppression. I have a slide on that for you that we'll look at in just a moment. But otherwise, everything looks as to be expected for the other ones. The effects get a little bit smaller, but they retain the same direction. I also have a bivariate R standardized effect that came out of those. And then I have a bunch of different versions of that over here. So STD is the column that I got from the z-score version of the model, or standardized effects. R is calculated from the t value, as shown right here. SR is the semi-partial correlation that's supposed to be the correlation of y with the unique part of x that doesn't have to do with any of the other x's. This R square is the square of that R, and this is the squared semi-partial eta whatever the hell that came out of the SAS output. That technical term there, whatever the hell SAS told me. So these two columns are in a squared metric, whereas these are in a unsquared metric. Actually, this one looks like the minuses got left off somehow, but it's absolute value. But they're not the same. So in terms of trying to report an effect size for these models, it gets tricky. There's no right answer here. I can tell you what's most common is the standardized column. And I think that's because the program spits it out for you. And you can z-score. Where this one becomes less helpful is when you have interaction terms in your model. Because if you try to compute a standardized coefficient for an interaction term, it matters whether or not you have the interaction term have its mean 0 and variance 1, or take each of the, or standardize each of the pieces and then multiply them together. They end up with different numbers depending on the order of operations, and it's not entirely clear which is right. So this is to tell you that there is no such thing as standardized. Not really. All of these things that are supposed to convey the same information differ a little bit. So as I suggested in here, just be clear which one you're reporting. Pick one and go with it. But don't just call it a standardized effect. Say if it's standardized, then it comes from this formula. If it's the R computed from the T, it comes from here. The semi-partial correlation is something that software will provide for you directly. And then if you're in a squared metric, this one comes from the software directly. This one is the square of that I just did for comparability. But here is your example results section. Most of this is describing the lead up, what happened in separate models, and then the model that's joint would be here. Now note the last sentence here. Emphasize why it matters based on your research questions predictors had significant unique effects. That's the part that I can't give you. So any of these results sections that I've given you are sort of a-theoretical. They're just describing what happens. In practice, you would want to write it to foreshadow or remind people like why it is what you're doing. So as hypothesized, the effective age remains significant after controlling for these things. Or as hypothesized, gender still matters after factoring in grip strength. Those kinds of things. Ideally, you would have questions that this provides the answers to. And so then not just interpreting what each of these things means in terms of slope language, but saying why it matters and why it answers your questions. That's the part that's contextual that's important. Okay. So in your homework, because of this difficulty in trying to figure out how to get the same standardized effects across programs as well as the difficulty in which ones they are, I'm not asking for them. Fair? Because yeah, Stata only gives certain things, SAS only gives certain things, and so R square is universal. Standardized effects are probably the most common. I was all excited about semi-partial R square until they didn't work for a categorical predictor. Who knows? So now you know enough to do your homework. And I have just a few more things to talk about before we have time to go. So let's pick up on slide 20. This is still lecture 6. We'll finish this up today and then be ready to start interaction terms. So this is just a disclaimer to remind you, in order for model results from general linear models with multiple predictors to be accurate, these are the things that have to be plausible. The residuals. So the part of y that's left over after accounting for your predictors, they're supposed to be independent, they're supposed to be normally distributed and have constant variance. So here are your fixes. If they're not independent, you need mixed effects or multi-level models. Those are the other classes that I teach. If you don't have normal or constant variance, you need generalized linear models. That's coming next semester. And if you need both of these things, that's actually what I'm doing in my multi-level class right now, multi-level generalized models. So never fear if these things are not plausible. It just means you take whatever you're learning right now and add more stuff to it to be able to fix those problems. The other things that we are working with is applicable to any linear model using an observed variable. So an observed variable is something that you have measured directly in your data set. There is such a thing as an unobserved variable or a latent variable. That's also coming higher order in statistics. But we are assuming that all of these variables are measured without error. To the extent that each of them have error, their relationships are going to be diminished. We're assuming that their effects are specified in the correct form. In other words, that we haven't missed any nonlinear effects of quantitative variables. We haven't lumped together groups that should be separated. or that we haven't specified any, there's no missing non-additivity or interaction terms. That's where we're headed next. And anything that you have not included is assumed to have a slope equal 0. That one you can't test because you can't put in an effect of a predictor you didn't measure. So you just got to make an argument as to why you couldn't measure it or why it shouldn't matter, or that's a direction for future research. That's my personal favorite. That's beyond the scope of this paper. All right. So other things that can happen to you. This is one of my favorite reviewer comments. Multicollinearity. Have you heard this word before? Yeah, it doesn't mean anything. This is not a thing. So reviewers will also complain about evidence of multicollinearity. See also collinearity with 2 L's. I still don't know which is correct. All Word Office documents yell at me when I type these words anyway, so it yells equally for 2 L's and then 1. Or collinearity or multicollinearity. What are they whining about? Well, the standard error for a predictor's slope when you have more than one predictor in the model, let me go back to this real quick, will be greater to the extent that your predictor has less unique variance. So the less unique information in your predictor, the harder it is to figure out its unique contribution, the bigger its standard error is going to be. That's just math. Once upon a time, this was a big problem. It's not anymore. People whining about multicollinearity, they're just worried that your predictors are really related to each other. Mathematically, that's not a problem. Once upon a time, I think when people were doing these models by hand, like you could get into numerical stability problems because of rounding errors and things like that. That's not a thing. So just don't worry about this if people mention this. Software will give you diagnostics as to when this may happen. Tolerance is the amount, is the proportion of unique variance. So if your predictor has less than 10% of its variance that's unique with respect to other predictors, that's supposed to be bad. Variance inflation is 1 over tolerance, so these things are related. This is not a thing. The only thing that is a problem is when you do something silly. Like you put in 2 variables that are literally the same thing. So if you have a test, say, that has 3 subscales, and you put in the 3 subscales as predictors, cool, not a problem. But if you add the total score of those 3 subscales, it will blow up because you just saturated it with completely redundant information. So the term for that is singularity. When they're singular, they're one and the same. So don't put in predictors that are carbon copies of each other. Now that could happen by accident. It could be that 2 predictors that aren't the same are actually perfectly correlated, in which case they'll completely knock each other out. But that would have been caught by troubleshooting your correlation matrix to begin with. So whenever you're running these models, staring at a correlation matrix to make sure that things are related but not super duper the same is a good step. So long as it's correlation less than 1, play ball. Problematic participants. Now this one is tricky because I can see the rationale, but it makes me very squishy to apply it. So squishy is another technical term. It means like uncomfortable. Like it makes me squishy. So here's a picture stolen from your textbook.
I just laughed like 4 minutes later. Like
Yes, it makes me squishy. Yeah. Like when my husband puts his dirty clothes in the basket that's reserved for clean clothes instead of the dirty clothes basket. That makes me squishy because that's just incorrect, right? It's like, meh. Those sorts of things. But so here's an example scatter plot with a regression line. Where the line comes from, it's the one that collectively minimizes the sum of squared residuals. So all of these little offnesses from the line is the one that makes the sum total of those the smallest. That's the principle of least squares that all these formulas and stuff are based off of. But that doesn't mean that the sum total line works for everybody. So why are people off their line, and does that matter? So one way that they can be off their line is that the line can work really badly for them. So distance is terminology that's used to describe individual cases that have a large E. So if we look at the value for C, where they are versus where they're supposed to be, that's a pretty big E. For this case, it's a lot bigger than some of the other cases. So this may be diagnostic in that we might want to look at if there's anything in common the cases with really large residuals have that we might be able to do a better job in the model by factoring in what they have. A is also a little bit problematic. Leverage is what it's called when people have extreme values on the predictor. So B out here is very far away with respect to X than all of the other ones. So they would say that they have high leverage. Influence, though, is the thing that we have to worry about, which is the impact on the slope. And in this case, C is the point that is likely to have the most influence. Like if you look at where the line would be without C, it looks like it would go up, it would be steeper. Like C is bringing it down. So points that have a big deal of influence on the solution are sometimes suspect. There is a diagnostic you can ask for to be saved in your data set as Cook's D, which is what the slope would be without that case. Like if you left each one out and made a new slope, and the ones that make the slope move a lot are considered problematic. However, what to do with them then is not clear. So you could imagine this purpose being used nefariously, right? Like, I want my line to be taller, so you're gone, you're gone, you're gone. Like sort of, trimming like the dead leaves off of your bush to make it look as nice and pretty. It's like, well, but don't you want to know why this person is so far off? Like, was there a data entry error, or is this like a real value and we just did a really bad job in measuring this person? So this is a situation in which if you're going to dump cases, you're going to have to be very clear about why and be prepared for people to yell at you and say, what would have happened if you kept them in? So I ended up doing this in my dissertation. There were 3 cases out of 155 that like completely changed a couple of sets of results. And they were so extreme relative to everyone else that I had one set of results with them and one set out because I wanted to like make the point that if it weren't for these 3 people, I would have a different story to tell. So the more cases you have, the less likely you're going to have this problem, but it's just something to acknowledge in terms of doing your troubleshooting. But it doesn't necessarily mean you start chucking people because that becomes problematic, I think. So those are more words that you may hear about. This is a word that we just talked about, suppression. That is when the relationship that shows up as a unique relationship is either larger or different in sign than its bivariate relationship. So we saw this for dementia. So there are mathematical proofs that you can say when this is going to happen. So if you have 2 significant bivariate relationships that are positive, the the unique relationships between them will be different if any of these 3 things are true, and it's if they're negatively correlated is the one that's probably the most common. So for instance, I stole this example from the Cohen regression book. Let's say that we have one predictor that's assertiveness, another predictor that is record-keeping diligence, and the outcome is sales success. So obviously assertiveness would be good for a salesperson, so would being diligent about keeping your records. However, are people who are assertive good at keeping records? So they had a data set in which the correlation between assertiveness and sales was 0.4, record keeping and sales was 0.1, but the 2 predictors were negatively correlated, so it fell under this category. So then what happened in terms of their standardized coefficients is that the effect of each of those was greater relative to its bivariate relationship. Because the other act as a suppressor in getting rid of sort of common variants that would make it look like they're less related. So this is just to say that the idea that your unique effects will be smaller than your bivariate effects is true most of the time, but not always. So That's the word that goes with it when things end up weird. Suppression. Here's another thing that can happen that can end up weird. Multivariate power. So I stole this example from one of my former colleagues at Nebraska. Here is a correlation table where I want to focus you on the first column. Here's Y and a correlation with 5 X's. This is from SPSS output where the p-value is the second entry. And what do you notice here? None of the predictors are significantly related to the outcome. So you would think that putting them in a common model wouldn't do any good. However, putting them together actually results in a significant R-square. Each of these predictors is not very correlated with the others, and when you put them together, their unique effect looks bigger because of there's less information. Let me say this here. When they have little correlation, each of them can contribute uniquely bigger. So it is indeed possible to have a significant model with no significant correlations behind it. Now they're sort of borderline, like a couple of these are significant and others aren't, but it is possible. So just to know that when you're looking at bivariate correlations, it may be the case that they could still contribute to the model even if they're negative. And here's the one that I think is my favorite. Oh, not this one. That's coming next. This is my second favorite. This is a phenomenon known as null washout, also stolen from the same place. So I have considered 9 predictors here, where only one of them is correlated with Y. So P1 is correlated, 0.2, it has a significant relationship. If I put all 9 in the model, P1 retains its significant relationship. But look what happens to the model. The model R-square is not significant. Now, how can that be? Because this F-test is asking about the amount of information divided by 9, right? It's like the average contribution of the 9, known over unknown. And the other 8 are dragging it down. So you'd be better off just having one thing by itself than 8 things that don't matter. Think of this as like a group project, right? Where an instructor puts you in groups to work together, because in theory then you only have to do like 1/9 of the work, but you get paired with 8 shitty people and you end up doing everything. Yeah, and it's more work to like corral all the 8 shitty people than if you had just done it yourself in the first place. Yeah, think of that. Yeah. And then this one, this can happen too. Significant model with no significant effects. So each of my predictors by itself is related to Y. Look at the correlations among them. 0.7, 0.7, 0.5, This is what reviewers would worry about with collinearity, right? All these predictors are relatively highly related to each other, such that when you ask what does each do in common, or excuse me, what does each do uniquely, nobody gets credit. It looks like nobody cleaned any rooms, yet somehow the house got clean. How can that be? Common. R-square still has the common part in it. Common doesn't get attributed to any of the individual predictors, but common goes into R-square. So it is possible to have a significant R-square that appears to have been created by nothing. Nothing uniquely got credit. And so this is the sort of situation in which reviewers would whine about multicollinearity, because clearly these things are sort of knocking each other out. But they do work together to create a significant prediction. It's just really hard to tell what each is doing to the story. All right. So, summarizing. For any GLM with multiple slopes, we want to know, does each slope contribute? We can get the p-value for the univariate wall test that goes with the t. We can get an effect size to try and describe it, such as a standardized coefficient, an R-value, a semi-partial correlation, semi-squared, etc. Is the model significant? We can check for the f-value that tells us that, which means our R-square is greater than 0. The model's effect size is R-square in that case. If we're talking about combining predictors, we want to know if each slope is still significantly different than 0. We can check with the same methods. And the effect size for each slope, unique effect, you have all of these things to choose from as one way to do that. So, the end. Yay. So it's not all that different. Just putting everything together at the same time and letting them fight it out. You will see a lot of research questions phrased that way. What is the effect of blah? Is there still an effect of blah after considering blah blah? Yeah. So you know where we're headed next time? Interactions. Do you know why I'm excited about that? Because that is where I have to start in all of my advanced classes because no one had been taught that before. And I have to waste like a month teaching them things that should have been in their introductory materials. And now, after you guys, I'm going to be able to start with the advanced stuff when you come to my advanced classes. It's going to be awesome. Plus, moderation is what we're going to be talking about. Have you guys heard that buzzword before? Moderation is a thing. People give workshops on it. People write books on it. It's not hard. It's interaction terms with a hell of a marketing campaign behind it. So that's going to be one more important set of words that you can add to your toolbox. You can do moderation analysis. Okay? It's going to be awesome. All right. Questions before we adjourn? All right, then I shall see you on Thursday. Go ahead and start your homeworks if you're feeling ambitious, and let me know if the Bitcoin people come back or you otherwise encounter problems.
Was that just